Learning never stops, and it is up for grabs. Good day, learners! Join me as I guide you every step of the way in learning mathematics the fun way. After going through this video, you are expected to generate patterns. Specifically, you will. Number 1, generate and describe patterns. Number 2, find the next few terms of a sequence. Number 3, find specific terms in a sequence. And number 4, find the general or nth term of a sequence. Let's start with our first activity. Follow the pattern. Fill in the next term for each item below. Number 1, egg, caterpillar, pupa, blank. Correct! The answer is butterfly. Item number 1 describes the life cycle of a butterfly. Let's go to number 2. J, F, M, A, M, J, J, blank. The next letter is A. Item number 2 are initials of the months in a calendar. Number 3. Triangle, square, pentagon, blank. You are in the right track. The next figure should be a hexagon. In item number 3, the numbers of sides of polygons are increasing. Let's go to number 4. 2, 3, 5, 8, 13, blank. 21. Each term resulted from getting the sum of two numbers that precedes it. Number 5. 5, 8, 11, 14, 17, 20, blank. Indeed, the answer is 23. We simply add a constant number 3 to each term. In the activity, we use repetitive characteristics or traits to predict future events or situations in happening. We call these as patterns. In mathematics, sequence is a special type of pattern being used to identify the missing number in an arrangement. A sequence is a function whose domain is the set of positive integers. It also means an ordered list of numbers. Each number in a sequence is called term. A sequence is finite if its domain is the set of positive integers 1, 2, 3, up to n, with the last term n. Example, in the sequence 3, 4, 5, 6, 7, the first term is 3. The second term is 4, while the fifth or the last term is 7. Since the sequence has the last term, then it is a finite sequence. A sequence is infinite if its domain is the set of positive integers 1, 2, 3, and so on, without a last term. Example, in the sequence 2, 5, 8, 11, and so on, the first term is 2. The second term is 5, and so on. Since the sequence has no last term, then it is an infinite sequence. An ellipsis, represented by 3 dots, is used to signify that a sequence continues. Finding specific terms in a sequence. In finding specific terms in a sequence, simply evaluate the sequence by substituting each positive integer 1, 2, 3, 4, and so on, depending on the term position being asked. For instance, to find the first 3 terms of the sequence a sub n is equal to 3n minus 2 we substitute n is equal to 1, 2, and 3 to the given formula. If n is equal to 1, which is our first term, we write first the given formula. A sub n is equal to 3n minus 2. Then, we substitute the value of n. So, we have here a sub 1 is equal to 3 times 1 minus 2. Then, perform the indicated operation and simplify. And we arrive at the answer of a sub 1 is equal to 1, which is our first term. If n is equal to 2, we follow the formula again. Write the given formula, a sub n is equal to 3n minus 2. Substitute the value of n. We have a sub 2 is equal to 3 times 2 minus 2. Then perform the indicated operation and simplify. We arrive with the answer of a sub 2 is equal to 4, which is our second term. And if n is equal to 3, we write again the given formula, a sub n is equal to 3n minus 2. Then, substitute the value of n. A sub 3 is equal to 3 times 3 minus 2. Perform the indicated operation and simplify. So we arrive at the answer of a sub 3 is equal to 7, which is our third term. Therefore, the first three terms of the sequence with the formula a sub n is equal to 3n minus 2 are 1, 4, and 7. How about if we look for the 5th, 11th, and 20th term given a different formula a sub n is equal to 5n plus 1? Using the same process, we will arrive with the following answers. First, we write the given formula a sub n is equal to 5n plus 1. We use 5 as our n, indicating the 5th term. Then, substitute the value of n. Then we perform the indicated operation and simplify our answer. We arrive at a sub 5 is equal to 26, which is our 5th term. If n is equal to 11, we write the given formula a sub n is equal to 5n plus 1. We substitute the value of n. A sub n is a sub 11 is equal to 5 times 11 plus 1. We perform the indicated operation and simplify, and we arrive at the answer of 56, which is our 11th term. If n is equal to 20, we write the given formula a sub n is equal to 5n plus 1. Then we substitute the value of n, perform the indicated operation, and simplify, and we arrive at the answer of a sub 20 is equal to 101, which is our 20th term. Finding the common difference in a sequence. To determine the common difference in a sequence, subtract any term by its preceding term. Given the sequence 8, 14, 20, 26, 32, we assign 8 as a sub 1, 14 as a sub 2, 20 as a sub 3, 26 as a sub 4, and 32 as a sub 5. Any of these terms can be subtracted by the preceding term. Thus, D is equal to a sub 2 minus a sub 1, which is equal to 14 minus 8, which is equal to 6. D is equal to a sub 3 minus a sub 2 equals 20 minus 14, which is equal to 6. D is equal to a sub 4 minus a sub 3 equals 26 minus 20, which is still equal to 6. And D is equal to a sub 5 minus a sub 4 equal to 32 minus 26, which is still equal to 6. As we can observe, the common difference denoted by D of the given sequence is equal to 6. Any pairs of the terms can be used in determining the common difference of a sequence. However, you must bear in mind that not all types of sequences have a common difference. Deriving the formula of finding the general or nth term of a sequence. Finding a term of a certain position in a sequence is much easier if we know the process of substitution. Now, what should we do if we will be asked to create a formula for finding the nth term of a given sequence? It would be very hard if we are to look for a certain term which position is too far from the first term. Say, we are asked to get the 25th, the 50th, or the 100th term. Thus, a formula is of a great help. Generally, if we are to look for the value of any term position, it will be equal to the first term, which is a sub 1, plus one term fewer, whatever we are at, n minus 1, and then multiply to the common difference d. In symbols, we write this as a sub n is equal to a sub 1 plus the quantity of n minus 1 times d. If the value of a sub 1 and d are given, it would be very easy to find any term in a sequence using this formula. Finding the general or nth term of a sequence examples. Number 1. Given the sequence 9, 11, 13, 15, 17, and so on. The difference between each term is 2, so d is equal to 2. While the first term, a sub 1, is equal to 9. Since we are looking for the formula of the nth term, we only substitute the values of a sub 1 and d. A sub n is equal to a plus 1, a sub 1 plus n minus 1 times d. So we substitute the value of a sub 1 and d. A sub n is equal to 9 plus the quantity of n minus 1 times 2. Then we simplify. A sub n is equal to 9 plus 2n minus 2. And we arrive at the final answer of a sub n is equal to 2n plus 7. Therefore, the nth term or general term of our sequence 9, 11, 13, 15, 17, and so on is a sub n is equal to 2n plus 7. Example number 2. Given the sequence negative 6, negative 11, negative 16, negative 21, and so on. The difference between each term is negative 5. So d is equal to negative 5. While the first term, a sub 1, is equal to 6. Substituting these values, we get a sub n is equal to a sub 1 plus the quantity of n minus 1 times d. A sub n is equal to negative 6 plus the quantity of n minus 1 times negative 5. By simplifying, we arrive at the final answer of a sub n is equal to negative 5n minus 1. Therefore, the nth term or general term of our sequence, negative 6, negative 11, negative 16, negative 21, and so on, is a sub n is equal to negative 5n minus 1. Now that we are done with today's discussion, I would like to remind you that you have to answer all the activities and exercises found in your module. This has been Teacher Malaya saying every best decision in life requires someone to have a critical mind and a loving heart. Empower yourselves with mathematics because math matters.